Alright guys, today we are going to go over acids and bases as well as how to calculate pH, pOH, concentration of H+, and concentration of OH-. So today we are going to focus on something called Arrhenius bases and acids. There are several different definitions, but this is going to focus solely on the Arrhenius acids and bases. For our definition, an acid is going to be any substance that contains H+ ions when dissolved in solution. A base is going to be considered any substance that contains OH ions when dissolved in solution. So we can identify if something is an acid or a base just by using the formula. All right, so when we look for the formula, we want to remember a couple of things. First, we want to remember that the positive ion is always written first. So if you're looking for an acid, you're looking for an H+ to be at the beginning of the formula since it is a positive charge. In a base, it'll always contain an OH negative ion or a hydroxide ion, and because that's negatively charged, we will find that at the end of the compound. So when I look at my formula here, I'm looking specifically for an OH- or an OH to be at the end of the compound. This presence of an OH means that it's going to be a base. Here I have H2SO4. The H+, I know they're positive because they're at the beginning of the compound, are found here at the beginning, making this an acid. HCl, again, I see that I have H's at the beginning of the formula, which indicates that my H has a +1 charge and is an acid. Now, when I see something like NaBr, notice that it doesn't have any H's or OH's in it. If it has neither, that means that it is neither an acid nor a base. One thing that we want to take note of is that our definition says that an acid contains H+ ions in solution. Same thing with the base. We're looking for OH ions in solution. Now, because it's a solution, that means that there's a solvent, and that solvent is typically water. Water is unique because water is comprised of both an H+ and an OH ion. So there are some H+ ions and OH ions in every single solution. Therefore, even if it's an acid, we still have a little bit of OH present due to the presence of water. If it's a base, we have a little bit of H+ present just because of the fact that it's dissolved in water. When we are talking about pH, pH is a scale that we are familiar with. pH is used to indicate how acidic or how basic something is. What pH is really measuring is the concentration or molarity of H+ ions in solution. Molarity is how we measure our concentration of something. It's moles per liter. If you're not sure about molarity, you might want to check out my other video, which is linked above. But molarity is going to tell us the concentration of H+ ions dissolved in solution. The higher the concentration of H+, the lower the pH value is. So what we see is that there's a mathematical relationship between the molarity of H+ and the pH of a solution. pH is just telling us how much H+ we have in a solution and thus how acidic it is. So mathematically, we can easily see this relationship if I write my molarity of H+ in scientific notation. If I write this in scientific notation, this number is equal to 1 times 10 to the negative 1. This molarity is equal to 1 times 10 to the negative 2, 1 times 10 to the negative 3, and 1 times 10 to the negative 4. So when we write it in this format, it's easy to see the connection between molarity and pH. The molarity of H+ is equivalent to the exponent. So mathematically, in order to get from our molarity to our pH, all we are doing is taking the negative log. Our pH is equal to the negative log of the concentration of H+. Now, one format thing that we use is that when we are referring to the molarity of H+ or the concentration of H+, or the concentration of anything for that matter, we often put it in brackets, which means the exact same thing as this capital M or molarity. This brings us to the pH scale. So if we were to look at a pH scale is going to range anywhere from 0 to 14. And right in the middle of that scale is 7. When we have a pH of 7, that is considered to be neutral, a neutral solution. It is neither acidic nor is it basic. Anything that is in the 0 to 7 range is going to be considered an acid, and anything in the 7 to 14 range is going to be considered a base. Now, it's important to remember what pH is measuring. It is just measuring the molarity or the concentration of the H plus ions. So when we have an acid, a low pH like 1 indicates that we have a relatively high concentration or molarity of H plus. If we have a base, that is going to indicate that we have a high concentration of OH minus. If I have a high concentration of H plus, it's an acid, but remember that due to the solvent being water, there are also OHs present. When it's an acid, there is a very low concentration of OH, and when it's a base, likewise, even though we have a ton of OH minus ions in solution, there are still some H plus ions as well. But we have a relatively low concentration of H plus ions when it's a basic solution. We have some equations that we can use to help us get from concentration or molarity into pH. So I have all of the equations listed here. It would be a great idea to write these down so that you can reference them in the future. pH can be found by taking the negative log of the concentration of H plus. Likewise, if we have a basic solution rather than an acid solution, we're going to be focusing on the concentration of OH minus. We can find something called the pOH by taking the negative log of our OH minus ion concentration. Now, if we are given the opposite, so if we are given a pH value and we want to get a concentration, we can use this third equation here in order to essentially undo the log. We can take 10 raised to the negative pH, and that is going to give me the concentration or molarity of my H plus. Likewise, if I have a base, I can use pOH to determine the concentration of OH minus in solution. One helpful way to connect our pH and our pOH is by knowing that our pH and our pOH will always add up to 14. All right, I am a very visual person, so sometimes having a flowchart or a graphic that I can look at helps me to make a connection between all of these equations since there are so many of them listed over here. Here we know there's a connection between H plus and pH. We can get from our H plus concentration to pH by taking the negative log of the concentration of H plus. Likewise, I can do the exact same thing with my OH minus concentration. I can find the pH by taking the negative log of my OH minus concentration. Now, if I want to go the other direction, and I want to go from pH to H plus, I can do so by taking 10 to the negative pH. When I do that, it'll give me the concentration or molarity of H plus. In the same way, I can go from pOH to OH minus by taking 10 raised to the negative pOH. There's one last important connection here, and that's between our pH and our pOH. My pH plus my pOH will always equal 14. So these are the equations that are going to help me convert between pH, H plus, pOH, and OH minus concentration. All right, my first problem asks, what is the pH of a 0.0005 molar HCl solution? First thing I want to do is decide if I have an acid or if I have a base. HCl contains an H plus, which means that this is going to be considered an acid. The next thing I need to consider is what the HCl is going to do when I put it in solution. My HCl is going to break down into H plus and Cl minus. I always want to consider how many H pluses are going to come from each of my acid molecules. So here, I know I'm going to get one H plus for every one HCl. And because of that, I know that my concentration of H plus is going to be exactly equal to the concentration of my HCl. Next step is to figure out where I am starting and where I'm going. So I know the molarity of H plus. I know this value right here, and I'm trying to find the pH. In order to get from molarity to pH, this tells me that I need to use the negative log of the H plus concentration. So in order to find pH, I need the negative log of the concentration of H+. I'm going to plug in the value that I know, which is 0.0005. And when I do that, I end up with a pH of 3.30. This makes sense because I know that I started with an acid, HCl, and the pH is below 7 as expected. Let's take a look at a second problem here. This time I want to know the pH of a 0.0000325 molar NaOH solution. Again, the first thing I want to do is determine if my substance is acidic or basic. So when I look at the formula, the presence of OH indicates that this is going to be a basic solution. Now, I'm trying to find the pH, but notice that when my NaOH dissolves in water, I'm going to get an Na plus and an OH minus. So I am going to be dealing with OH minus concentration. Because every one NaOH produces just one OH minus, the concentration or molarity of my OH minus is going to be exactly the same as the concentration of NaOH. Now I know my concentration of OH minus and I'm trying to find my pH. Notice that there's no direct connection between these, but I can use my OH concentration to find pOH. And once I know pOH, I can connect that to pH using the equations here. So let's go ahead and tackle this. First step is to get from OH minus to pOH. In order to do that, it tells me that I need to take the negative log of my OH minus concentration. pOH is equal to the negative log of the concentration of OH minus. I know the concentration of OH minus from up here, so I'm going to plug it into my equation, and when I do that, I get a pOH that is equal to 4.49. Now, that is indicating my OH concentration, but I need to express this as a pH value since that's what the problem asked for. My pH plus my pOH are always going to equal 14. So all I need to do is substitute in what I know, and I know my pOH is 4.49, and I know that when I add these two together, it is going to be 14. That means that my pH is going to be equal to 9.51. So this number makes sense. I know that this is a base, and on the pH scale, I expect a base to be above 7, and the pH is above 7. All right, my next problem asks what is the OH minus concentration in a solution with a pH of 8.4. I'm starting with a pH value. That means I'm starting right here. I'm trying to get to an OH minus concentration. So there's no direct connection between the two, but I can use my relationship between pH and pOH in order to figure out my OH minus concentration. I know that the pH is equal to 8.4. And if the pH is equal to 8.4, then I know that my pOH must be equal to 5.6 because my pH and pOH must always add up to 14. Now that I have my pOH, I can find my concentration of OH minus by taking 10 raised to the negative pOH. So my concentration of OH minus is going to be equal to 10 raised to the negative pOH, which is 5.6. We don't want to leave it in this format. Instead, we're going to plug this into our calculator and get it into a decimal form so that we don't have decimal in our exponent. When I plug this in my calculator, I end up with 2.51 times 10 to the negative 6 as my molarity of OH minus. All right, let's look at another example. This time, I want to know the OH minus concentration in a 0.2 molar CaOH2 solution. Just like before, we need to first determine if this is an acid or a base. So when I look at my formula, I see OH on the second half of the compound, which indicates that it has a negative charge. So my OH negative tells me that this is going to be a base. Now, if you notice, this indicates that we have two OHs. This is an important consideration. When you have a substance that you are dissolving to determine if it's acidic or basic, I would always consider what it breaks into when it dissolves. I have CaOH2, which means that I'm going to get a calcium plus 2 in solution, but I'm also going to get 2 OH minuses. There are going to be 2 OH minuses for every 1 calcium. This is important because now my concentration of OH minus is going to be double the concentration of the original calcium hydroxide, since I get 2 OHs for every 1 CaOH2. From the problem, I know that the molarity of CaOH2 is 0.2, but I also know that I'm going to get 2 OHs for every 1 calcium hydroxide. That means that if I want the concentration of OH minus, I am going to have to multiply this by 2 to show that there are 2 OHs for every 1 calcium hydroxide. That means that my concentration of OH minus in this case is going to be 0.4. Double the concentration of the calcium hydroxide. That is all this problem asks for, so we are done. All right, let's look at a little more complicated problem. Remember that these acids and bases are all solutions. That means that our molarity equation, molarity equals moles over liters, as well as our dilution equations may come in handy in conjunction with our pH and pOH problems. All right, the very first thing we want to do is to look at our formula and determine if we have an acid or if we have a base. The fact that I have OH on the end of this means that it is going to be a base. The next thing I want to do is figure out where I'm starting and where I'm going. So in this case, I have grams and I have liters. The end goal is to find the pH. So I know I need to find the pH. I don't have a molarity of either H plus or OH minus in this problem. That tells me that I'm going to have to get that molarity before I can determine the pH. Because this is a base, I know that I'm going to be dealing with OH minus ion concentrations. There's no direct connection between my molarity of OH minus and my pH, so I'm going to have to go through pOH. Let's start by getting that OH minus ion concentration. It's important to remember that we can calculate molarity by taking our moles over our liters. I am going to list all of the variables that I know from the problem. I know that I have 3.4 grams of aluminum hydroxide. That 3.4 grams will connect to moles, but I'm going to have to do a conversion prior to using my equation. My liters are 2.0. If I know moles and I know liters, I can solve for that last unknown variable, which is my molarity. So let's make sure that we have the right units before we plug it into our equation. In order to convert from grams to moles, I'm going to go to the periodic table and I'm going to add up my aluminum hydroxide's molar mass. When I do that, I get 78 grams is equivalent to 1 mole. I can use dimensional analysis to show how many moles form. This is moles of aluminum hydroxide. All right, now that I know all of the variables except for molarity, I'm ready to solve. Let's substitute in what we know. Molarity is equal to my moles, which is 0.0436, over my liters, which is 2.0. This is going to give me a molarity of 0.02179. But this is our molarity of AlOH3. It's important to consider that we want the molarity of just OH here, not AlOH3. So we have to figure out what our aluminum hydroxide is going to do in solution. It's going to break down into its positive and negative ions. That means that I'm going to end up with an aluminum that carries a +3 charge, and I'm going to end up with 3 OH minuses. That means I'm going to get 3 OH minuses for every 1 AlOH3. So the concentration of my OH minus is going to be triple that of my AlOH3. When I triple that value, I get 0.0654 as my molarity of OH minus. Again, my molarity of OH minus is triple that of my aluminum hydroxide. Now that I know my OH minus concentration, I'm ready to find pOH. I can find pOH by taking the negative log of my concentration of OH minus. When I solve for this, I find that my pOH is 1.0 0.18. Remember that my pOH and my pH will always add up to 14, so I can find my pH by simply subtracting 1.18 from 14. That is going to give me 12.82. pH was my end goal, so I know that I'm done now. Again, my answer makes sense because this is a base. I would expect the pH to be greater than 7, and it is.